seems I found the right way to do a presentation in this place. To do it to start from the end. But I didn't do it just because because of a random choice. Because some practical considerations. Sorry.
No, because of the mass maybe.
Yeah, so on the first few days I was in the talks and it seems that not every talk is easy to get to the end. But in my talk, I want to get to the end because the end is some important part in the end. So that's one reason. The other reason is that I always feel tired and exhausted in Friday afternoon talks after like very many inspiring and illuminating discussions. So maybe we should try something fun and maybe to engage you to join this game. So this game is the following. I will present all my slides backwards. Even my transcripts are attached to the slides. So you will hear me refer to some slides I presented before that I haven't presented. And this is a hard game because many things you haven't seen will be referred to as if they have been shown. So this is not so. The right attitude towards this game is to have some fun. And if you don't understand something, I will be available after the conference. Is it universal invariant? Let's see. There are some messages that show up very symmetrically. And also there's video recording, and also there are papers. You can play it backwards, exactly. Okay, let's get started. Okay, let's go. The game starts. Thank you for your attention.
Before that, we should.
And so this slide is for acknowledgement. So administratively, I have a quantum foundation, quantum information background, and I started my academic career doing researching quantum indefinite causal structure. But I always had an interest in quantum gravity, and these are my teachers for quantum gravity. And I would like to thank these people for doing the previous works that inspired me to develop this new approach to quantum gravity. And I'd like to end this slide with an observation. It seems there's lots of Italian names, incidentally, on this slide. Okay, here's the summary of my talk. So I presented a correlational formulation of quantum information, and one application is a general characterization of processes using correlation constraints. These include processes with indefinite causal structure. And the next, I moved out to quantum field theory. I presented a new perspective on Feynman diagrams. They're not associated with the perturbative theory in my understanding. This new understanding is that they're topological classes of correlational configurations. So this is my understanding of the physical meaning of Feynman diagrams. They appear even if you do quantum information. And thirdly, I presented a new approach to quantum gravity, the world quantum gravity. It is a non-perturbative Lorentzian path integral approach. The basic idea is very simple. Instead of using a field variable GAB defined pointwise, we use a relational variable sigma, the world function, which is the squared invariant distance. This is defined for pairs of points, x and y. This is the distance. And using this change of variable, we had a formula for world quantum gravity. This approach has these following three features. It's UV regular for both gravity and matter, matter quantum field theory. I put the seams here because this is still manuscript in preparation, and I'm 80% confident in the results. And the second feature is that it's space-time singularity free. The third feature is that it's efficient for computation. The complex amplitude becomes real and positive after we perform the Hardy sum. And because of these properties, it's suitable for numerical Monte Carlo calculation. And for all these three features, indefinite causal structure plays a crucial role through the Hardy sum, which is summing over time-like and space-like separations, and this results in the cancellation of divergences and imaginary parts and negative parts. So I just presented to you a modal-dependent argument for the UV regularization in this approach to quantum gravity. So the question is, how general is this result? So here I want to put quantum information into action. I want to offer a conjecture that the UV divergences are killed by indefinite causal structure, even in discrete theories, such as loop quantum gravity or causal set. So it's possible that divergences are killed twice. First, by discreteness. Second, by indefinite causal structure. And I want to do this argument. This is a conjecture, but I have some motivations for this conjecture. The first conjecture is that indefinite causal structure appears generically in theories admitting a path integral formulation. The argument is as follows. If you start with a classical space-time with x and y on the boundary, the causal relation will be one of the three, x preceding y, y preceding x, or x and y causally separated for an individual classical gravitational configuration. In a quantum theory, you do a path integral, so you're summing over all the gravitational configurations in the bulk, and you're having a linear sum of these three causal structures. So in this sense, you're having a superposition of causal structure as long as you do quantum gravity using a path integral, and there's no miraculous cancellations of the effects. So indefinite causal structure, I would argue, appears generically in theories of quantum gravity. And next comes the information theory argument. So I want to do a modal-independent study of indefinite causal structure on the correlations. I use the process matrices.
Question?
Yeah. Can I?
Sure.
You want? The general question: do you expect that in the path integral there would be histories where there is no causal structure to speak of, that is not indefinite, as in superposition of two definite ones, that there is simply no causal structure?
I wouldn't expect it on a general one. Maybe in particular theories, it's a modal-dependent thing.
Would you like to have such histories in your sum, in your theory?
You mean no causal structure at all? So my understanding of space-time is that it comes with causal structure. So it's not clear to me what is a space-time without a causal structure. And so I want to present this modal-independent result from studying process matrices with indefinite causal structure. And the result is the following. If I study process matrices with a large superposition, such as a quantum switch with large superposition of different causal structures, then the finding is that quantum correlations are generically reduced continuously to zero with the increasing causal structure quantum fluctuation.
I also have a question. So here you give this intuition that 2 points can be in three possible relations. We had a lot of discussions how much we can identify points operational and all this. Are you talking about this in the previous slides?
No. So one can identify points, say, through scalar field values, like in Lucien's idea, the coincidence of scalar fields.
So these are not manifold points.
These are physical points, physically meaningful points. And then from this modal-independent study, we see that correlations are reduced by introducing indefinite causal structure. And the argument is that if we have indefinite causal structure in a generic path integral approach to quantum gravity, we expect also the cancellation of the reduction of correlation in the UV. Okay, so these are the three features I want to show in this approach to quantum gravity. UV divergence free. Actually, this should be UV regular. Actually, okay, these are the three aspects I want to study. And also I want to study singularities, and I want to study how you evaluate this approach to make predictions, quantitative predictions. And always bear in mind this picture. For the approach to quantum gravity, you start with a matter Feynman diagram. You introduce extra dashed edges for gravitational degrees of freedom. These are the blue edges, and they have these blue correlators. They're analogs of Feynman propagators. And then your old Feynman propagators for matter are broken into smaller pieces. These are these. They're modified by gravity as well. And then you have this formula similar to the ordinary Feynman rules. And the orange part is, as I introduced on the last slide, the integration measure for your path integral for gravity. And the idea is to do the Hardy sum over different causal structures and study the small distance limit and examine the UV properties. And the first finding is that strikingly, if I start with the complex amplitude, because of this Hardy sum over different causal structures, things cancel out. I end up with a real and positive number. And this is efficient for Monte Carlo. And this is without taking the UV limit. The second finding is that after I take the UV limit, there's the gravitational propagator is finite. It is 1. There's no UV divergence. The matter propagator still has a pole, but that's because we haven't considered the measure for the path integral for gravity. After we take into account the extra factor of S here, we multiply S to these propagators, even the matter UV divergence is cancelled out. We got a finite number. And the third finding, so the second finding is that it's UV divergence free, both in gravity and in matter. And the third finding is that now we want to ask about space-time singularity. So we take the infinite curvature limit. And that corresponds to the S going to 0, so the length on each edge going to 0 limit for all the edges. And in this case, we see that this whole amplitude goes to 0. So what does it mean in a path integral approach to quantum gravity to have no singularity? Because we're summing over all the gravitational configurations. So in this scenario, it means the singularity configurations have 0 amplitude. They don't contribute to your path integral. Okay, so we are going to use the Hardy sum to study the UV properties of the theory. So what is a Hardy sum? It's very simple. It's consider x and y. They're in possibly two causal relations, either time-like or space-like. The Hardy sum is just to sum over these different parts. Recall that the path integral measure for this case is defined in this following way. And the important part I want you to focus on is the red part, which is an integral over different geodesic distances. The positive part corresponds to space-like separation, and the negative part corresponds to time-like separation. By doing this integral from a negative number to a positive number, we're summing over both parts. And this holds for a general function of f as a function of sigma. We break it into two parts, and then change variable from sigma to the geodesic distance s. In this case, we have a negative sign for one causal structure, and in this case, we have a positive sign for the other causal structure. And then we change variable, so sigma is second order in distance, so we get an extra factor of s when we change variable from sigma to s. And we have these two pieces. There's an extra minus sign that allows us to change the integration interval from a to 0 to 0 to a in the next step. And we arrive at this formula. Now, in this bracket, we have a summation of the original function in two different causal structures. And in this integration measure, we have crucially an important extra factor of S that help us reduce UV divergences. Both parts are important for this cancellation mechanism of UV divergences, real imaginary parts and positive and negative parts that I show on the next slide. Okay, now the main formula for this approach toward quantum gravity is the following. It's a bit complicated, but actually it's not very hard to understand the basic idea. We should focus on the red part in these two boxes. Alpha is proportional to the gravitational coupling. If you set alpha to 0, these red parts disappear. In that case, dk recovers the standard QFT propagator on classical curved space-time. This is the Schwinger proper time representation. And H becomes, question?
What are you defining? The partition function?
This is the partition function. This is the path integral.
Well, it should appear in the first box. Or what? The first box, there is no equality.
The first box is the partition function, on the left actually.
On the left is the matter QFT Feynman rule. So G is the Feynman propagator, V is the vertex factor, N is the symmetry factor, and we are integrating over different positions, and we are summing over different Feynman diagrams, gamma. And then we do this arrow and upgrade this pure matter QFT to quantum space-time.
What's the limit?
The limit is this stands for skeleton, so finer skeleton. This is the same with spin forms.
Sorry? What is?
But this is the partition function. So that's Z equal limit, etc.
Yes, this is the path integral result. And this limit is, so on a fixed skeleton, on a fixed graph, I have an approximation to the partition function. And the exact result is approached when we take the limit of finer skeletons. Okay. It's the same with the spin forms. And now if we eliminate the red part, H becomes 1. So there's no quantum gravity degrees of freedom. It's trivial. So we can recover standard QFT on curved space-time using this formula. And then this red part encodes the quantum gravitational correction. And among these factors, the important parts are delta, which is a measure of curvature. This is a variation of the Van Vleck-Moret determinant. And this is the only, I think, non-trivial piece. Yes?
Sorry, because this is a myth of the story. So is this postulated? And do you justify it by the limit of recovering QFT?
This comes from the Einstein-Hilbert action. And I'm not showing it on the slide.
It's derived.
It is not mathematically derived. It is a motivation. So it's postulated, but there's a correspondence to Einstein-Hilbert action.
See, we have 5 remaining minutes to get to the beginning.
Very good.
You cannot pull out questions at the beginning. Please don't take
So I think this is the last slide I really want to present. And after that, I can do a very fast fashion of slides. But this is the main idea of the world quantum gravity approach. It's a change of variable. So recall this basic definition of GAB, the metric. It's if you think about it, it's a bit strange that when in space-time we talk about space-time distances, but then when we do quantum field theory when we do field theory for gravity, we talk about this tensor field, whose physical meaning is unclear, and its physical meaning is the distance. It gives you the distance, but we're not using it when we do field theory. And so the idea of this whole approach is to take this physical meaning seriously. We want to use the distance as the basic variable. And so we take this infinitesimal squared geodesic distance, we integrate it over geodesics from x to y, for all pairs of x and y. This defines the Singe world function. I use this as a basic variable for this approach to quantum gravity. And this function sigma contains all the information of the metric through this formula. So the whole idea of this approach is to change variable from GAB to sigma, and then use sigma as a basic variable for path integral. So this is showing you a way to do a quantum field theory using a quantum information language through these correlation diagrams.
So this sigma, it looks like something like a Regge, idea of using basically in the continuous, right? Instead of using the edge lengths of some piecewise flat manifold, you're saying this is a continuous version.
One important difference is that there is no triangle inequality required, I guess.
Which simplifies things.
Simplifies things. Yes, and the basic idea, I guess, the other is that in Regge calculus, we start with a classical theory, a discretized GR, which is a classical theory of gravity. And then we do the path integral. Here, there's no classical discretization of gravity. Everything I propose is the correspondence is based on a trick discovered by Parker in the 70s within path integral. So we start with the quantum theory in the beginning. There's no classical theory. In the sense, it's not a quantization of a theory. It's a quantum theory from the start. Yes?
I have a question about that earlier slide. How do you go from the circle? No, that one. How do you go from the circle to the square? So there's in the Feynman diagrams don't have they're just defined by the topology, but now you're fixed to draw a square. So why don't you draw a pentagon or something else?
This is possible. So the topology doesn't matter.
Oh really?
Yeah. So all that matters is the number of is the topology of the graph that matters.
Okay.
But then how do you get the dynamical definition for these new variables? I mean, so you just propose something, and then you have some action for this, or a discretized action for the new variables? Or?
I start with the Einstein-Hilbert action, which is in terms of G.
Right.
And then there's a formula by Parker that allows you to change a variable from the Einstein-Hilbert action. It allows you to replace the Ricci scalar by this triangle, this Van Vleck-Moret determinant.
So what is S and rho then?
And S and rhos are scalars assigned to the edges. There are two real numbers. There are two real numbers on each edge.
So but you're only defining those dynamics for the discrete theory then, on the lattice. So you're not defining any continuum version of the dynamics. Okay.
And what's the difference between these numbers?
So S is the distance, rho is the scalar. Rho is the curvature. And in terms of in terms of dynamics, so this is similar to spin foam. I think it's exactly the same conceptual picture with spin foams.
Yeah, but I mean, in spin forms, you also come somewhat from an action that you use in order to motivate the amplitudes in the end. And so I'm just wondering if
Yes, I start with the Einstein-Hilbert action.
Yeah, but I mean, you do that in a continuum, but in terms of these new variables, you don't have an action for that.
I see. I see. Whether I have an e to the is for these variables. I don't have them. No.
But one very okay, of course, you have to see the paper to see what they're doing exactly. But you said that delta is replacing the curvature.
Yes.
Right?
Yes.
Delta is this sign C is an oscillating thing with infinite zeros, and you have a -3, so you have infinite divergences in there. Then it goes to an ln.
Think there's
which is
no
exponential. It seems to be a super complicated. So this is so there is a -3, and so you're dividing over infinite zeros there. There is infinite divergences in that delta, right?
So sync starts with 1 and then goes down to 0 at this point. And then, yes, and so the trick is I multiply with ln.
There is it's less than pi. Okay. So it's the finite usual that you have there?
Yes, this is a place where the caustic is reached. So
okay, so is there a divergence in the curvature or no?
no. Well, the whole thing. So if you combine everything together with the ln, there's no divergence, because delta only shows up in this form. There's no divergence for this formula.
Okay, we can.
May I suggest that we get to the
Good suggestion. Good suggestion. There are two things I want to emphasize. One is that one could use this formalism of correlation diagrams to do quantum field theory on classical space-time, but with a quantum information flavor language. And there's a general characterization of processes using correlation constraints that incorporates quantum indefinite causal structure. And this slightly generalized previous characterizations, such as in the process matrix framework. For example, within one single laboratory, we can have multiple subsystems, and we can impose constraints on who can signal to whom, and have a general characterization of the process matrices in this scenario. And it's a great pleasure to be here. Thank the organizers for giving me the chance to speak. I hope you will enjoy my talk.
Thank you. I'm sure that we will. And I think there is, even though we went a bit over time, I would say if there is a crucial question about some clarification that needs to be made now, I would allow time for that one.
You mean for the previous
talk? Yeah, that's right.
Sure.
Can you talk questions before the talk?
I have a very short comment.
Yeah.
It's amazing how well it worked backwards, actually.
Oh. Yes, I've never done this before, but
If there is no question only, I would say that,
Yeah.
that there is a story with John Archibald Wheeler that was carrying his transparencies and then about to start to run and fall down. Everything was like mixed. And then we were able to, how can we like order this? He said, doesn't matter. Whatever the order is, I will start.
Exactly. All right, so how should I say? Let's thank the